Hello, my name is Tianxun Hu from Simon Fraser University. I'm very happy to give this talk here about online schema evolution is almost free for snapshot databases, and it's a joint work with Tianzheng Wang and Qingqing Zhou. In relational databases, schemas define tables. For example, we can use this statement to create a table which has a schema with 3 int columns. But what if I want to change my schema? In fact, modern database applications often need to change their schemas as the application features continue to evolve. Such changing schema is so-called schema evolution. It's the process of changing the structure of a database, like adding a column, changing the column type, or adding a constraint to a specific column. It can be done with data definition language, DDL statements, like the alter table operation here. We will show you 2 examples later. In contrast, if we want to change table data, we can use the DML statements. The DML here means the data manipulation language. It's used to get or modify table data records. Some operations like select, insert, delete, and update. Here is one example. Let's say we want to add a column 3 with default value 0. The DB engine will copy each record and add a column on each record. So the final result is that we can have a column 3 with default value 0s. So the adding column here can be done by copy and transformation. The second example here is to add a constraint on column 2 to set it to be not null. The DB engine will then scan the values of column 2 to find if there is a violation. So here, if a null is found, it means there is a violation, so the DDL should fail. Otherwise, the DDL can succeed. So adding a constraint here can be done by verification. It's used to check each value to see whether there is a violation. So we have seen 2 examples. Actually, there are many types of DDL operations. But how exactly do we implement schema evolution? So I will talk about prior approaches firstly, then our approach. The first prior approach is the blocking approach. Let's just add a column example here. The blocking approach will put an exclusive lock on table first, then scans the whole table to add a column for each record. During this process, because of the exclusive lock, the DMLs will be blocked, which causes low concurrency, hence the low performance. The figure here shows the throughput per second in the micro benchmark. When doing DDL, which is adding a column here, the throughput of the blocking approach goes to 0. So the locking overhead is quite large here. The blue line here is our approach, which will be shown later. The second prior approach is the lazy migration. Let's use the same example here. The lazy migration will commit the new schema on table immediately without scanning. After that, the schema is new but the new columns have not been added. Then, there is a subsequent DML transaction access the second record and finds it has not been migrated yet. So, it will help to add the new column first, then do other operations later. With lazy migration, DDL can commit very quickly, but it cannot support verify or verification here because without scanning, such violations cannot be found. So the DDL commits quickly with lazy migration, but may lead to undefined behavior. So we have seen 2 prior approaches here. They are insufficient. The first issue is not online, like the blocking approach. The second issue is incomplete functionality, like the lazy migration cannot support adding a constraint. The third one is that most implementations are ad hoc. They will use triggers or views to do schema evolution. So schema evolution here is a database application itself, which is quite complex. The fourth one here is that many implementations are not transactional. For example, if we want to do dangerous operations like converting the varchar to int, then such operations must be able to roll back in case of illegal characters. So the fundamental reason here is that existing approaches are ad hoc patches. They are not baked in the engine design. So, because of the previous issues, we propose our approach, Tesseract. It's online, it's transactional, and it can provide native schema resolution support within the DBMS engine. Our key observation here is that a DDL is a DML that modifies the full table. It's so-called data definition as manipulation, DDAM. Based on this observation, a DDL can run in the way the DML runs. So we can slightly tweak the concurrency control protocol within the engine to handle the previous issues. And in our system, we will focus on the snapshot isolation. Because our method is based on SI, let's look at SI first. Under SI, each record has multiple versions. So for this example here, the listed version of the record is v3 with a timestamp 6. The timestamp here can decide the visibility. For example, there is a transaction with begin timestamp 8 can see this latest version v3 here, because 8 is larger than 6. And if the transaction wants to update the record, it will install a new version called v4. And under SI, the read and write don't block each other, so the update transaction does not need to wait for other transactions. And the v4 here is still invisible to other transactions because the transaction has not committed. And after some time, the transaction commits with a commit timestamp 9, and the commit timestamp will also be stamped to the new version v4 as well, and the v4 will be visible to other transactions. SI is adopted by all major OLTP DBMSs. We base our approach on a representative SI design, ERMIA. Other engines like Hackathon can also do snapshot isolation. In our system, a table has a primary index mapping keys to record IDs. Records reside in tables, which are indirection arrays. A record in a table has multiple versions as well, which are stored in an in-memory version chain, and such versions can also be persisted into underlying storage, like the log here. To read a record version, a transaction needs to traverse the version chain from the newest to the oldest, based on their timestamps. To update a record, if the transaction can see the latest version, then it will use the compare and swap to insert the new version to the head of the version chain. The full table scanning here means the indirection array scan from the beginning to the end. After we have known the background, we propose the basic data definition as manipulation, the basic DDAM. The core idea here is that the DDL transaction can be seen as a DML transaction that happens to modify the entire tables. For example, we can start the DDL transaction, and to alter the table, for each record in the table, that record will be updated with the new schema. And finally, we commit the DDL transaction. One thing to note here is that the code in black, like start transaction, alter table, and commit, are written by the users, but the code in red are implemented by the engine. So here, basic DDAM directly leverages the generic SI to do DDL. It looks very simple, right? However, the basic DDAM is still not good enough. Let's use the same example here. The DDL transaction starts to scan the table and update each record, while there is a DML transaction updates the first record and install a new version. And the DDL transaction finds that it cannot see the latest version of the first record, so it needs to abort. It's so-called write-write conflict. And because of the conflicts here, both DDL and DML can abort, so everybody loses. The reason here is that the DDL transaction is also going to update the same record and do transformation on the same table, causing the conflict with concurrent DMLs. So here we introduce the out-of-place migration to handle this issue. The out-of-place migration here means the DML transactions still work on the old table with old schema. And for the DDL transaction, it works on the new table with new schema. And such new table will be invisible to concurrent DMLs before the DDL commits. However, the DML transactions can still update the old table. So such new versions installed by the DML transactions should also be applied to the new table. So we introduce Change Data Capture CDC here to install such new versions to the new table. After the initial table scanning, the DDL will pre-commit to get a timestamp tpre. And after the tpre, the CDC job starts. So I will talk about the tpre here. It's when the new schema will become visible, but also it will be marked as unfinished. So later, the concurrent DMLs see this new but unfinished schema. They will wait here until the CDC job is done. The CDC job will simply apply the updates using the log from T2 to tpre. For example, there is a new table here, and there is a log which stores the new versions from the concurrent DMLs. And the CDC job will read the log and apply such new versions to the new table. But what if the new version or the change is incompatible? For example, a DDL is converting a float column to int. Meanwhile, a DML writes a record with decimal points, which is later detected by CDC. So what should we do here? We can choose to abort DDL, but the migration work can be wasted. Or we can choose to abort DML, which may lead to cascading aborts. To handle the cascading aborts, we can use the commit pipelining. The core idea here is that after the transactions pre-commit, they will be held up in the commit queues until the pending DDL is done. So results of such transactions will be visible internally, but not to the user applications. And if there is a violating DML transaction, we can simply abort all transactions after that violating DML transaction in the commit queue. So some innocent transactions can also be aborted in this way. So there are different trade-offs depending on which to prioritize. Okay, let's do some evaluation here. We have implemented Tesseract in Ermia, and our system runs in memory. We also assign some CPU cores to worker threads and some to the DDL threads. We use two types of benchmarks here, the YSSB-like micro benchmark and TBCC benchmark with additional DDL transactions. For the DDL transactions here, because there isn't a lot of benchmarks for schema evolution, so we devised some according to prior work as extensions to YSSB and TBCC benchmark. And such DDL transactions will be issued after 2 seconds the benchmark started. Let's take a look at micro benchmark with add a column again. For our approach Tesseract here, it takes longer time because of the TDC job, but it has low impact on the throughput. And for the blocking approach here, it's all about blocking overhead. And for the lazy migration here, because it's built in the application level, index needs to be rebuilt, and the DML also suffers to migrate data. For the TBCC plus DDL, it's so-called TBCCD results here. It shows the similar trend. The gap between the lazy migration and the Tesseract becomes smaller, but our approach, Tesseract, can still offer better functionality. I will make a summary here. Modern database applications need transactional and online DDL. Our key observation here is that DDL is a DML that modifies the flow tables. It's so-called data definition as manipulation, DDAM. Based on this observation, we proposed the Tesseract to do transactional and online DDL at the engine level by slightly tweaking the concurrency control protocol, like the out-of-place migration, change data capture, and relax the snapshots. Because of a time limit, I didn't talk about it, but without it, Tesseract still has some issues. For example, the snapshot can also become stale when doing scanning. So we introduced small tweaks to the SI protocol, which is the relaxed snapshot here, to handle such issues. You can find more details in the paper, and here is our code. Thank you for your attention.